welcome to PASC26. This is the highlights from the conference. I have the pleasure to have with me one of the two best poster awardees, Sam Altfield from ECMWF UK. You presented a poster on performance, portable and highly scalable spectral transforms with EC Trans. And before asking any other questions, of course, I need to first congratulate for these Best Poster Awards.
Thanks.
But also, can you tell us a little bit about your research, of course, presented in your poster?
Yeah, the poster is about a very old technique used in global atmospheric modeling, which is called the spectral transform, also called the spherical harmonic transform. This is an algorithm which allows you to transform between two different spaces. One is the grid point space, which is the space of latitudes and longitudes, very intuitive. The other one is a space where you can represent a global gridded field on the sphere as a sum of spherical harmonics. So you have a basis function there. And to go between these two spaces, which is done on every time step of our atmospheric model, you need a spectral transform algorithm. This can be very expensive, especially as you go to very high resolutions. And so it was one of the early targets for GPU acceleration. So my poster is about the latest efforts over the last couple of years in adapting this very old algorithm to the latest generation of GPUs. In fact, that was only the first half of the poster. The second half was all about data-driven techniques for weather forecasting, and certain applications for the same algorithm, the spectral transform, in those models, and how we're trying to bring that very old technique now even into PyTorch so that we can use it for data-driven weather forecasting as well.
Yes, of course, when you talk about data, we immediately think about machine learning, AI type of analysis, but we also heard that you know, this AI applied to weather forecast or to weather in general, they have no understanding of the physics. So they are just tools that we apply and that we somehow, that they show somehow that they can reproduce the weather and the climate well. But what are the challenges for for your community to apply AI, machine learning type of tools to your research?
Well, firstly, the success of the data-driven techniques in weather forecasting is really almost a fluke, because we use very similar techniques to video processing. So we basically benefited from all the advances that field has undergone over the last 5 to 10 years. Without that kind of thing, we don't have the resources to kind of develop a whole independent technique for weather forecasting. So we've kind of copied those techniques, and of course we've made some modifications to make them suitable for weather prediction. So the main challenges really are in finding ways to piggyback on the wider developments of data-driven science and artificial intelligence in general. That also applies to the hardware, of course. We're well beyond the period where a weather forecasting agency can specify hardware. We, of course, have to look at what is available on the market and try to find a way to use that as best as we can. And, of course, that means using GPUs effectively.
This is a very good news. I mean, there are a lot of efforts going on on porting some of the climate models to GPUs now since quite some time.
Yeah.
But then what I would like to ask you, how do you think, what is the future of the HPC, so the simulation part of weather and climate? Because I ask you this, we hear a lot, especially in the more traditional HPC environment, that sometimes they are afraid that the AI might replace completely the simulations.
Yeah.
What are your thoughts about this?
To be honest, I don't know the answer to that question, and I don't think I will know it for another 2 to 3 years, because the situation is changing so rapidly. To give you one example, some of my colleagues have only just recently successfully developed a fully observation-based AI weather forecasting system. Most AI-based weather forecasting systems are trained on a very large data set called a reanalysis. This is a long, consistent data set, usually 50 years or so, tracking the weather of every single day over those 50 years. And in order to build such a data set, you need a traditional weather model. So this was always the answer for the people like me who are used to using those models, who are promoters of those models. We always need those models because we need them to generate the reanalysis. Well, some of my colleagues have completely bypassed that. They've trained a successful weather forecasting model using only observations. So no model at all. And of course, if that's the future, then we do not need a traditional physics-based model anymore. That would be sad, I think, because we learn a lot from these models, and I think they're very elegant machines that we've constructed. There's been a lot of effort over the last few decades in building those models. It would be a shame to just throw them away. So my hope is that there may come some kind of application in the future that can only be done with those models, but right now, the future is very much uncertain.
Well, I think as you said, we still have a lot to learn about this machine learning and AI. Sorry, about this machine learning and AI. Of course, you might be right, and you might have to replace you might be able to replace with AI and observational data model. I mean, trained on observational data, but you never know. I mean, in science, new ideas are always coming to life. So maybe you will need simulation to address other important problems. But anyway, these are exciting times because there is a lot of unknown. So it means that there is also a lot of room for new discoveries and being surprised. So congratulations, Sam, again for your Best Poster Award, and see you maybe in the next PASC conference.
Yeah, I hope. Yeah, great.